Good day, guys. Alright, so in this video, I want to talk about 8.1 rotational kinematics. Alright, so we'll be doing a few things. The first one is for me to introduce to you a number of terms, 5 terms to be exact. Alright, and then after that, what I want to do is I want to relate, or at least I want to show you equations that relate between linear terms and rotational terms. Right. And then last but not least, I would like to present to you kinematic equation, but in the cases of rotations. All right. Okay, so let's look at the first one. The first term that we need to define is angular displacement, and then everything else falls and will be defined according to that. So angular displacement is, so if you think about displacement, right, we talk about a initial and a final position. It is the same case for displacement, only it is the case that you are looking at the angles between them. Angles between what, you ask? Well, if a body takes a circular path, right, then you will have a center of that circular path. If you draw the position of the body relative, a straight line from the position of the body straight to the center of the circle, what you have is the radius, right? And if you have the initial and the final position, you can find the angle between them. That is what we call the angular displacement. So let's have a little bit of a visualization. So again, we have a circular path. I am going to take the direction of anti-clockwise. Okay, so here's the initial position and here's the final position. If we draw lines from both those positions into the center of the circle or the circular path and look at the angle between them, we call that an angular displacement. Okay, and this angular displacement is measured in radians or rads. Okay, all right, so next we look at velocity, angular velocity, right? So just to remind you, linear velocity is defined to be the rate of change of displacement. It is the same case for angular velocity, where you have omega is equals to the rate of change of theta, which is d theta over dt. Okay, and again, it is quite similar in the sense that this is measured in units of radians per second per second, okay, which is rad per second. Now, if we take another derivative of that, which means you are taking the second derivative of the angular displacement with respect to time, right, we will get angular acceleration. So that's alpha equals to d square, d2 theta over d2 dt2 dt square, and that's the second derivative. That also means that it's going to be the first derivative of omega. Okay, and that is going to be measured in radians per second per second, twice that. Okay, so those are the terms that involves the word angular, and as as you notice, they all have the word radian in them. Now there are two more terms that are related to circular path or rotational kinematics, but they do not have the word angular in them, but they very much contribute to the circular motion. All right, and those two words are tangential acceleration and centripetal acceleration. They are both measured in meters per second, right? But they have different direction, and their direction will have 90 degrees between them. So if you think about it, tangential means it's going to be tangent, right? It's going to be tangent to the path, and then centripetal means to the center of the circle, and the angle between the AT and the AC is going to be 90 degrees. Okay, all right, so we have learned 5 terms and we want to relate them to linear kinematics. So let's do that. So just to remind you, in linear kinematics we have a number of terms. We have displacement, we have velocity, and we have acceleration. Okay, and we want to relate them to the new terms that we have just learned. Okay, that's going to be theta, omega, alpha, at, which is just a to be honest, and ac. So at and a is the same thing. And the equations that relate them are, first things first, we have our displacement, which is equals to s equals to r theta. The second one is v equals to r omega, and the last one to be well, not the second last one is going to be the tangential acceleration is equals to r alpha. And of course, the one that you've seen before in chapter 6, where we talked about circular motion, the centripetal acceleration is equals to v squared over r. And of course, this is equals to r omega squared, but you can get that relationship from the second equation. Okay? Alright, so what I want to do next is to talk about the equations, the kinematic equations, right? The rotational kinematics equation. Okay, so much like their linear counterpart, they also have three equations. If we had in the linear spectrum, right, in the linear spectrum what we had was v equals to u plus at, where u is the initial velocity, v is the final velocity, a is the acceleration, and t is the time, right? In the rotational kinematics, so rotational, what we have here is the omega final is equals to omega initial plus alpha t. That's the rotational counterpart for that equation. Okay, again we also have s equals to ut plus half at square, and we can get this equation as well for angular displacement, which is theta equals to omega initial t plus half alpha t square. And of course the last equation being v square equals to u square plus 2as. Then for the rotational counterpart we have omega f square equals to omega I square plus 2 alpha theta. Okay? Alright, so that's the end of 8.1. We have introduced 5 terms. We have looked at how to relate between linear terms and their rotational counterpart. And then we have also looked at rotational equations. Okay, so that is it for this video. Thank you very much, and I'll see you in the next video.